Welcome again. Today our topic on algorithms design and analysis course is algorithms design strategies. Algorithms design can be applied to a variety of contexts. It has become important for IT professionals to upgrade their knowledge in order to meet the growing industry demand. Algorithms can be classified or grouped according to different parameters, such as types of problem solved, deterministic, non-deterministic, design techniques. Some of common problem types are searching, sorting, string processing, graph network problems like shortest path, troubling salesman, combinatorial problems like finding a permutation, combination or subset, bioinformatics, and several others. Regarding the deterministic, non-deterministic classification, deterministic algorithms are the most familiar kind of algorithms. They retain the same answer no matter how many times it is called on the same data. Always take the same steps to complete the task when applied to the same data. While non-deterministic algorithms can exhibit different behavior for the same input data on different runs because of external state other than the input data or user input, timer values, random values, timing sensitive operations on multiple processor machines. Non-deterministic algorithms are often used to obtain approximate solutions to given problem instances, or when it is too costly to find exact solutions using a deterministic algorithm. The next classification is the design techniques. Selecting a proper design technique for algorithms is a complex but important task. In this meeting, we will examine different algorithm design techniques and their applications. The main algorithm design techniques are brute force, divide and conquer, greedy algorithms, dynamic programming, randomized algorithms, backtracking, branch and bound algorithms, and there are other strategies. A given problem can be solved using different approaches. Some approaches deliver much more efficient results than others by means of usage of resources, time and space complexities, user friendliness, maintainability, security, etc. We start first with brute force algorithms. A brute force algorithm blindly iterates an entire domain of possible solutions in search of one or more solutions which satisfy a condition. Brute force algorithms refers to a programming style that does not include any shortcuts to improve performance. They solve the problem by trying every one of a wide range of possible solutions. Examples of brute force algorithms: brute force search, troubling salesman problem, break a password, open a lock, and several others. Disadvantages of brute force algorithms: in many cases, they are not efficient by means of time and space complexities. Next, divide and conquer strategy. In the divide and conquer approach, the problem is divided into several small subproblems. Then these subproblems are solved recursively and combined to get the solution of the original problem. The divide and conquer approach involves the following steps. Divide: the original problem is divided into subproblems. Conquer: the subproblems are solved recursively, and combine: the solutions of the subproblems are combined together to get the solution of the original problem. Examples of divide and conquer strategy: binary search, quick sort, merge sort, integer multiplication, matrix inversion, matrix multiplication, and others. Here we have the advantages of divide and conquer strategy. It allows us to solve difficult and often impossible looking problems such as Tower of Hanoi. It often plays a part in finding other efficient algorithms like quick and merge sort algorithms. However, divide and conquer strategy has disadvantages as well. Sometimes it can become more complicated than a basic iterative approach. Recursive call uses stack where function state needs to be stored. Remember, please, whenever we use recursion, we need extra space. Sometimes more calculations are performed. For example, if we use a recursion function to calculate the factorial number, then extra calculations are performed. There are several variations of divide and conquer strategy, like decrease and conquer, transform and conquer. Here, the decrease can be by 1 or by a constant factor or a variable size decrease. Examples: binary search. And transform and conquer solve a different problem and get the desired result. Problem reduction sometimes perform some kind of pre-processing on the data. Examples: heap sort, searching on ordered and balanced trees. Next, a greedy strategy. According to greedy strategy, problem is solved in stages by taking one step and considering one output at a time to get the optimal solution. This strategy is called greedy because when an optimal solution to the smaller instance is provided, the algorithm does not consider the total problem as a whole. Once a solution is considered, the greedy algorithm never considers the same solution again. The greedy strategy is very easy to apply to complex problem. It decides which step will provide the most accurate solution in the next step. As the algorithm proceeds, two sets are accumulated. One contains candidates that have already been considered and chosen, while the other contains candidates that have been considered and rejected. The choice made at each step is feasible, satisfies constraints, locally optimal, best choice at each step, irrevocable. Examples: coin changing problem, graphs applications like Dijkstra shortest path algorithm, Prim's minimum spanning tree algorithm, Kruskal's minimum spanning tree algorithm. The main disadvantage of the greedy strategy that it does not always guarantee the optimal solution. However, the solution may be close to optimal. For example, in the 0-1 knapsack problem, a greedy approach does not guarantee the optimal solution like in dynamic programming. Next, dynamic programming. Dynamic programming is a bottom-up approach in which all possible small problems are solved and then combined to obtain solutions for bigger problems. It is the most powerful design technique for solving optimization problems. The main difference between dynamic programming and divide and conquer strategies is that in divide and conquer strategy, the problem is partitioned into disjoint subproblems. Then these subproblems are solved recursively and the solutions are combined to solve the original problem. While dynamic programming is used when the subproblems are not independent, e.g. when they share the same subproblems. In this case, divide and conquer may do more work than necessary because it solves the same subproblem multiple times. There are three basic elements that characterize a dynamic programming strategy: substructure, table structure, and bottom-up computation. Substructure decomposes the given problem into smaller subproblems, express the solution of the original problem in terms of the solution for smaller problems. Regarding table structure component, after solving the subproblems, store the result to the subproblems in a table. This is done because subproblem solutions are reused many times and no need to repeat the solution for the problem several times. The third basic component, bottom-up computation. Here we use the generated table to combine the solution of smaller subproblems to solve larger subproblems and eventually arrives to a solution to complete problem. Dynamic programming is used in different areas such as 0-1 knapsack problem, mathematical optimization problem, all pair shortest path problem, reliability design problem, longest common subsequences, flight control and robotics control, time sharing, mainly CPU scheduling. Next strategy is backtracking. In backtracking, we start with a possible solution which satisfies all the required conditions. Then we move to the next level. And if that level does not produce a satisfactory solution, we retain one level back and start with a new option. In backtracking, the problem is solved in a recursive manner. It is a systematic way of trying different sequences of decisions to find the correct one. It figures out the solution by searching the solution space of the given problem methodically. Backtracking is an optimization technique to solve combinational problems. It's applied to both programmatic and real-life problems. Usually, backtracking follows the depth-first search. Examples: 8-queen problem, Sudoku puzzle, and going through a maze. Next strategy is branch and bound. Branch and bound is a strategy used in discrete and combinatorial optimization problems and mathematical optimization. A branch and bound strategy is similar to backtracking and is used to solve optimization problems, only minimization. It looks for the best solution for a given problem in the entire space of the solution. The bounds in the function to be optimized are merged with the value of the latest best solution. It allows the algorithm to find parts of the solution space completely. The purpose of a branch and bound search is to maintain the lowest cost path to a target. Once a solution is found, it can keep improving the solution. Branch and bound usually follows the breadth-first search. Here is a comparison between backtracking and branch and bound. I mentioned some of them. Backtracking solves the problem by finding a solution to the first subproblem and then recursively solving other subproblems based on the solution of the previous ones, while branch and bound solves a given problem by dividing it into at least 2 new restricted subproblems. Branch and bound is more suitable for situations where we cannot apply the greedy method and dynamic programming. Usually backtracking is faster than branch and bound, and I mentioned that backtracking follows the depth-first search, while branch and bound follows the breadth-first search. Creating an algorithm design and choosing the best design strategy for a particular problem is an art that requires a good understanding of each strategy, its strengths and weak points when applying it to each type of problems. The environment and constraints for solving the problem should be considered as well. For example, some strategies solve the problem with less time but require extra memory, while others may solve the problem with less space requirements but they do need more time. Selecting the proper strategy for solving a problem is an open area of research. Thank you.